Good morning. Good morning, everyone. Welcome to today's research salon. And I'm going to present a paper titled Usable User Authentication on a Smartwatch Using Vibration. This paper is published in ACM CCS 2021. And here is the outline today. I'll first give the introduction and talk about attack models. Then I will show the proposed methods. Then it goes to the evaluation and conclusion. So to begin with, we have witnessed the prosperity of the smartphone usage. It's recorded that millions of shipments are made in 1 quarter of year 2020. People can use the smartwatches to make payments or to monitor your health and make and answer the phone calls. Many of these usage are not requiring the pair to a smartphone anymore. So nowadays, the smartwatches are smart and not just some auxiliary devices. So as a result, all these devices should be well protected. There's a need for an authentication that verifies the valid user. So using a password can cover most of the cases, but it requires user interaction and sometimes become inconvenient. For example, when the valid user is driving, putting in some passwords can distract the driver. And furthermore, the password can be stolen, and even the valid user itself may forget the password. The other direction is to use some biometric authentication, such as the fingerprint, face recognition, vein recognition, and the iris. This seems to be good to test someone's identity, but the interactions are still needed. You need to put your fingers on the touching pad or lift your arm and stand still to capture the face recognition. Some special sensors are also needed, maybe not equipped on devices like smartwatches. And all these biometric are static authentication methods. So we still, in some paper, we can still find some spoofs to attack such biometric traits. For example, we can use some 3D printed, some fake fingerprint, or to wear some contact for the iris recognition. So you can still say the biometric is not enough. And in this paper, the author adopts a new challenge response structure. So simply speaking, it just means it authenticates via the reaction to some random stimulus. In this paper, they find the vibration can be an appropriate challenge for a smartwatch. Where the user is varying, the body will absorb and reflect, propagate those vibrations generated from smartwatch. So the current motion sensors can collect the like the accelerometer and gyroscope will collect the readings, and they can measure the response of this random generated vibrations. But the challenge remains because the sensors on a smartwatch will have a very low sampling frequency. It is reported to be as low as 100 Hertz for the Apple Watch. And the vibration frequency itself is also in low frequency. But before talking about the specific design to stress this issue, let's summarize the contributions first. The first one is they propose the first approach to analyze the response to vibration from a smartwatch, and the independently authentication without the help of the pair to the smartphones. and there is no additional devices needed, and there require no action that the user must take to complete the authentication. So here are the summary of contributions, and let's move to the attack models. The first attack is called not-in-wear attack. When the target user takes off the watch and put it on the table, the attacker will come and steal the information. So in my perspective, it's just a super careless user. So I won't talk about it too much later. And another attack is called impersonation attack. The attacker is pretend to be the target user. So they have two methods. The first method is to capture the previous vibration response. It is pretty hard to conduct in reality, but we just assume the attacker can do that. And we call it simulation attack later. And for the second method, it is described as the attacker will find someone or himself very similar as the target user in several physical structures. For example, the height, weight, body fat rate. So it may generate a similar response and pass the authentication. So here is the second method. And I will cover the proposed method in three parts. The first is the author proposed a two-phase authentication, and second, how they generate the signal and how they measure the response. And the third part is the user verification process. So the first phase of this authentication is the vibration enrollment phase. This enrollment phase happens when a new user empties his pocket and finally buy the new watch. He can't wait to try them out, but the system let him wait and measure some response first. So the responses are saved and used for further authentication. So it extracts the feature from the user's response and train a classifier for the further use. And after the enrollment process, every time, for example, the user makes a payment, it will jump into the authentication phase. So the smartwatch generates 5 random type vibration signals and verify their response. Even one response is invalid, the smartwatch will not authenticate. So here is the figure shows the process. Every time when the user wants to authenticate, the smartwatch will generate some random vibrations, and this the response to these vibrations are used to fed to a classifier.
So I have a quick question here. So when the user try to enroll, the smartphone try all those types of vibrations?
Yeah, it tries all types of vibrations.
Okay. So could you go to the next page? Next page.
Okay.
Yeah. In this case, for example, I'm not sure. No, previous one. So in this case, I'm not sure. Say, if a human body, you know, if we regard the human body as a channel, right? So if it's a static channel, I don't have any problem. It's going to pass all the authentications. I mean, what I'm talking about here is a legitimate user, right? It's going to pass all the challenge response process, authentication process. In case human body is kind of dynamic channels, for example, during the summer, you have more sweat or something, your heartbeat faster. During the winter, you eat a lot, your heartbeat beat a lot slower, kind of slower. So is that going to affect this, you know, challenge and verification process?
Well, I don't think this will challenge. This will influence the challenge vibration process. Of course, the challenge and the challenge itself is vibration generated from the smartwatch. So the only thing they care is when I put my smartwatch on my wrist, on my hand, or the vibration it generates will propagate through my bone or skin, and it can reflect back to the accelerometer or gyroscope. So it's only related to the bone structure, I would like to say, or the skin, the position you put it. If it does, it can cannot make a significant difference if the user is legitimate user himself. When it's in summer or in winter, it doesn't matter.
Even say, because when we wear iWatch or whatever watch, we cannot put the watch exactly the same position every day, right? For example, today, and tomorrow the position is kind of a little bit different. All this kind of noise, wrong position stuff can be tolerant, right?
Yeah, they didn't mention that in later for the slight differences, the position you're wearing the watch, but they said it doesn't matter, and makes the verification process still pass.
Okay, I think I need to learn more how they can pass the verification processes. They use a similarity or they use some other things, yeah.
I'll cover it later.
Okay.
So let's move on to the signal generation and measurement. So here are the process. The first step is to generate some random vibration sequence chosen from the system offered official vibration types. Also take Apple Watch, for example, it has 9 official vibration types, and they call it vibration challenge. And then followed by a filtering process. It means it will remove the noise under 20 hertz from the human movement. And in the third step, the statistic features and pairs of peaks and heights are potential features to be extracted for training. And you can see the table 2 and find the feature list. So, but are those features appropriate to distinguish participants? Intuitively, the author makes a scatter plot to see whether the dots are from the same participant associates or not. And they visualize it using random forest to use to visualize the 2 most important features. And they compare it to the famous MFCC, that means the male frequency capture coefficient, very popular features in speech processing. So we can see when the sampling frequency is set at 48 kilohertz, both of these features are associated together. But the things are different when the sampling rate is at 100 hertz. So we can see for the statistical features, they still associate well, but for the MFCC, they associate loosely. It doesn't, because doesn't make sense since MFCC is proposed to filter human hearing perception, and if the sampling frequency is so low, it cannot work it cannot work well. So the verification model is here is a multi-class model plus a binary model. So the multi-class model uses the default users and the new users data, and they adopt a random forest classifier and output a probability vector. And afterwards, this probability vector fed to a binary model and use the FEM to classify whether or not this user is valid or invalid. So before coming to the evaluation, are there any questions?
How is the overall data sampling process? It's like the smartwatch cause some vibration and wait for a while. You know, those signals get through the bone or something, and it's bounced back or something. Then the smartwatch collects the receiving signal. Is something like that?
Exactly, and it doesn't wait too. It doesn't need to wait for a while because their sampling rate is low. They just start them at the same time, so they start the vibration and begin and read the accelerometer and gyroscope at the same time.
Mm-hmm.
So they can verify the either the vibration type and the user's response. So they use the user response to verify whether or not this user is valid.
Okay, allow me to ask a stupid question. Although I use a smartphone every day, actually, I'm not very familiar with the smartphone inside. So the motion sensor, right, the gyroscope or whatever, it's only the sensor to sense the vibration. It works like a receiver, right?
It is designed for some to sense the motion, but yes, it does work as a receiver.
Yeah, in this work, it works like a receiver. But
yeah.
How the smartwatch generates the the transmission signal? How can the smartwatch generate a vibration? I mean,
they have motors inside. For example, you receive an email, it will vibrate to remind you, or you set an alarm, it vibrates, right?
Okay, it's different from the gyroscope or any kind of motion sensor, right?
Yeah, it's a transmitter. It vibrates to notify the user.
Okay.
Yeah, so in this work, they are trying to make it a transmitter, and the receiver is can collect the response from the user.
But
so they are two different devices.
From a receiver end, can the receiver distinguish, the vibration caused by the motor in the smartphone, and the signal, go through or say reflect by the bones? Can they distinguish that?
Because they almost happens in the same time, so they just record when this vibration begins. So your bone and skin will slightly change the original signal. So it has some channel information and maybe some pass loss at different frequency bands. So using these features, they can distinguish the specific user. But I'm going to say it not trying to separate the transmitted signal and the received signal.
So when you do the learning things, the transmit signal is kind of mixed with the receiving signal, right?
Yeah, but they do not care the pure transmit signal.
Okay.
Because in the enrolling phase, it's the mixed signal, right?
Okay. In the enrollment phase, it's mixed signal as well.
Yeah.
So when they do the verification, okay, so it's not necessary to filter out the transmission signal. Okay.
Yeah.
Okay, thank you.
So let's move on to the evaluation. First, I'll show the experiment setup. So this experiment is done on Apple Watch Series 3 with 9 default variations and 100 Hertz sampling rate. And for the participant information, they recruit 20 participants and measured 150 response per user. And you can check the participant information listed in table 3, like the physical indicator like the height, weight, body fat rate. So here are all the information from the participants. And the performance metric in this task is the equal error rate, and most found in some speaker verification task. So let's talk about the FNR, the rate of false rejections. It's used to evaluate the usability, and for the FPR is the rate of false acceptance, and it's always used to evaluate the security. The author then put the confusion matrix to claim their features and probability vectors both distinguish the vibration type and the participant. So I'm not going to put the confusion matrix there, but I want to mention that the score is pretty close to 1. So for your question, Dr. Pan, the vibration type and participants can be distinguished using this method. And then the user authentication is tested by setting the first participant as the first 5 participants as the default user. So it is saved before shipment. So it's like some pre-installed data. And the second, and one of the remaining users is chosen to be the valid user, and the rest are all attackers. So this figure shows the overall result. The red curve shows the false positive rate, and the blue curve shows the false negative rate. The x-axis is the decision threshold. So if we move the threshold, we can have different FPR and FNR. So according to the EER, because we are using the EER for this metric, so we pay attention to the cross in this figure and set the threshold at the 0.8630. So at this threshold, we will have the equal FNR and FPR, while the solid the dotted blue line is from the second experiment on different days. So both in these 2 experiments, we can find the average FNR for the first and second measurement is quite low, under 0.01. So this method can be regarded as usable. And for the impersonation attack, the performance the author select from the participant and pair those have very similar physical indicators. For example, the height, weight, it turns out that the verification can work and they have very small FPR. As for the simulation attack, at first, as I said, it's very hard to perform. And they also discuss those kinds of attack with which capture the previous response. We cannot pass the random challenge. So it because every time you generate new random vibrations, so even you capture the previous vibration response, you will not pass the authentication. And they also have some other experiments shows the participants move their bodies and put their hands in their pockets. They said this proposed method is also robust to this kind of impact, and the verification result is still good. So at last, let's draw a conclusion. So the author proposed a vibration-based user authentication methods for smartwatches based on the challenge response structure. And evaluate on Apple Watch 3, low EER of 0.0137 can be produced. And this method is robust against various attackers. So that's all. Thanks for your attention. And I'm welcome to, I'm open to answer all the questions you're concerned about.
Any questions?
Hi, Chenpei. I have several questions. The first one is, what's the relationship between the vibration type and the response?
It's just a challenge response, right?
Yes.
For example, you have when you have different types of vibrations, and the response is just the gyroscope readings when you wear the smartwatch on your when you're wearing the smartwatch. So it means if you are generating different vibration types, the response is also different, right?
Yes, but and on the experimental page, you said you have 150 types of response. So for each vibration type, we have different response.
No, it doesn't the type. It's just some repeated experiment.
Okay, just a repeated experiment.
Yeah,
So if the type of the response is the type of the vibration is the same, so the response should be similar, right? Or different.
the types of response is same. That means when you want to distinguish this type of response with others, it's a kind of classification. And if you want to use the response to distinguish this user from other users, the features are this is a different story, right? So, I I mean, uh, because each person is we assume that each person is unique, and the response to the same vibration can be different. So it has some potential to distinguish it from other users. So it's similar, but it can be distinguished.
Okay, got it. And the second question is, can you turn to the multi-classification page?
Uh,
Yes, here. What's the meaning of use default users and the new user data?
yeah,
What's the meaning of this new user data? So for example, if we have already have 5 users, so we have the 6 users data, or what's the meaning of this new user data?
yeah. In this page, for example, the ABCDE is the default user. We have 5 default users. They are not from the user enrollment. They are pre-installed in the smartwatch before it ships to the new user. So before enrollment, it already had some data from the default user. And the enrollment process is to let this new user to register his data. So the classifier will be trained according to this in total 6 users.
Okay. So it seems like a adoption phase, right?
Mm,
To okay.
yeah, if you have you have so many default users, you will have a very good performance. But in this figure, it's just showing example.
Okay, so if we have a model which can distinguish 5 users, and if we don't enroll the new data of the 6 user, so if in this situation the 6 user is coming, can we distinguish that this user is invalid, or it should be classified to 5 users?
I don't know what you mean, because the 6th user is the valid user need to be enrolled, right? So this 5 user is actually is invariant, and we only need to enroll our valid user as the 6th user. So why we need to distinguish our valid user from the default user?
I mean, if someone else wears the iWatch, so can we distinguish that this user is invalid or not?
Okay, that's the second process, right? That second phase. After the valid user enrolls, when there's another person, like, for example, his attacker is wearing a watch, and because the classifier already been trained, so it will be classified by the binary model, and it will be distinguished by as the invalid user. So we will not authenticate in this case.
Okay, I got it. So the first phase is that this user should be classified to one of the 5 users, and then we can have our binary model to distinguish this user is invalid or not.
Yeah.
That's the okay.
So when the new signals arrives, we only care whether or not it's a one by one classification. We only care is valid or invalid. So we do not care about the multi-class anymore.
Okay, got it. And the last question is that what's the type of the received signal? Since we have 2 types of the machines to get the received signal, so what's the type of the received signal?
Yeah, we have 2 different devices, but the signal has 6 channels. For the accelerometer, it has XYZ axis, and for the gyroscope, it's still 3 axes. So in total, we have 6 channels.
Okay.
And we train them, yeah, it's just one signal with 6 channels.
Okay, with more features. Okay. All right, thanks.
You're welcome.
Chenpei, I have another 2 questions. Could you go to the sample rate page? Like
this one?
Yeah, a previous one. Yeah, this one is 48 kilohertz, right? Khertz, and they're using 100 hertz, right?
Yes.
But it seems if we can sample like 48 kHz, MFCC algorithm can work well, right?
Yes, it does work well.
But why do we need very low sample rate for that?
It's not we need low sample rate. Actually, it's because for the smartwatch, it only offers a very low sample rate. Because the gyroscope and accelerometer are designed to track the motion. So the motion will not have higher frequency. So it only need to be lower than 100 hertz.
Okay, it depends on the gyroscopes. Yeah, in other words, depends on the sensor, right? So motion sensor detection stuff. Okay.
Yeah.
So could you go to the motivation page, which you have the face recognition areas and stuff like that? Yeah, basically here you can say, okay, we launch a very complicated attack. For example, for areas, you use a contact lens or something. You need to make the contact lens very, complex so that you can pass the authentication. I mean, for this one, can we say we can record someone's vibration features? We do the replay attack. It's very easy, right? You just generate something like, I don't know, a small motor or something, just vibrate at the same frequency, right? If you put it, yeah.
Yeah, it's not that easy because in their paper, they mentioned it as a simulation attack. So that means because all these features, why I mentioned this biometric is because I want to say this authentication or static method. So you can take your time to fabricate some for some 3D printing or some fake arrays. But for the vibration, for this paper, they are proposed a challenge response structure. So every time the challenge is random, even you can you can record some previous vibration response. You cannot pass this time because this entirely is a totally new challenge. So you cannot pass them with the old response. It's a dynamic things, something like that.
I mean, no, overall, you know, so the only thing you rely on here is your kind of biometric feature. Is on it depends on your bones, right? Depends on bone structure, or say the blood fluid or whatever. Depends on the things happen on your wrist, right?
Yeah.
What I can get probably is in other words, it's just another channel. Right? If I can perfectly, I don't know, reconstruct this channel, then I can definitely, it doesn't matter your you know, input signal is kind of random challenge or something, I can pass your authentication.
But it's hard, right? How can you reconstruct this channel? It's human body.
Yeah, that's true. But for example, your iris is also human body, right? But actually you extract certain kind of feature, and when you launch the attack, you use a contact lens. In the contact lens, you reconstruct those features. You know what I mean? Yeah, I think.
Yeah, but every time you check this the iris, because it's never changed, so you can have the time to vary in the.
But the thing is, you know, in your paper, your channel is kind of static too. Your wrist is static too. Again, it's similar to the expressway we're doing, right? So every time we have the same pipeline, every time you have the same wrist. Right?
That's true.
Use a lot of signal, and based on the output and the input signal, I can definitely kind of reconstruct the channel. If you follow that channel, it doesn't matter if the feature is a vibration or something. Say major feature is a vibration, for example. I can use a small motor to vibrate at the same frequency, or you know, according to your wrist feature.
I still don't think it's that easy to launch this simulation attack, because the vibration itself, you're trying to use another transmitter to let the receiver have a plausible result. But in this case, the smartwatch itself has the transmitter. If it also vibrates, so how can you at the same time generate a vibration signal that will satisfy the verification?
No. I'm not trying to imitate your input signal or whatever. I just try to imitate your wrist.
I think it's hard.
Yeah, I believe it's hard, but it's not like it's not like it cannot be compromised, right? Because you know, when the iris coming out, people say, okay, iris cannot be compromised, but afterwards, people know the structure of the iris. How can they do the authentication? Then they produce something like the things you show here, the contact class, you know, contact lens, right? They have the similar structure. They can pass the authentication stuff, right? So what I'm saying is probably, but here you extract many features, right?
Yeah, they all statistic features.
Yeah, you want to satisfy all the features. Probably that's not easy. But actually, those things are statistical feature. For example, root mean square error, standard deviation, screwness. That's all statistical feature, right?
Yeah.
I mean, we need to figure out the major thing. For example, iris, it depends on your eye structure. That's the most important thing, right? The eye structure is the most important thing. Your fingerprint, it depends on the structure of your fingerprint. Okay, your voice, it depends on the voice pattern or something. It's not like I mean, for all those kind of signals, you can extract all these 15 features. That's only the statistical feature. So the things we need to capture is what's the most important things for your wrist. Is the bone structure make sense, or is the blood running over there in your wine? Does that make sense? What is the most important thing? If we can reproduce that feature. Yeah,
it is hard to answer because this paper is based on some experiment. So I'm not sure whether or not they have some studies to show what structure is dominates the response type.
I'm not trying to think your answer. I'm gonna try to discuss with you, right? Because if you check the false positive ratio or something, I will say actually it's lower than the fingerprint and iris, right? So if for iris and the fingerprint, we can extract the most important feature and reproduce them. I don't think for this wrist, we cannot do the similar thing.
I know what you mean, Dr. Pan.
Yeah, it's much less complex than the iris eye structure or say the fingerprint stuff, right? Supposedly.
Yeah, I think so.
Yeah, also the learning algorithm they use actually is much simpler compared to the iris recognition or say the face recognition or something.
Yeah, actually they're using the random forest and SBM.
Yeah, but think about that. I mean, fundamentally, you know, if we know the truth of your wrist, right? the ground truth of your wrist, which one makes the dominant, you know, impacts or something, then probably we can reproduce the attack. Similar to the iris recognition or something, because the learning model here is very easy, right?
Yeah, I know what you mean. Yeah, it means actually we need to find out the ground truth of what actually makes this this vibration response unique.
Yeah, exactly. So what matters in your wrist making this kind of a, you know, vibration response unique? Then we find that a dominant factor, then I think we can launch the attack, right?
All right.
But I know it's difficult, but I just want to say probably that's something, one direction, if we want to further doing this, we can look into. Just like the old days when the iris recognition coming out, people say, okay, it's 100%, you know, unique biometric feature. There's no attack for that. But later people find it out, you know, you can compromise it.
Okay.
Yeah. Okay.
I have a question.
Go ahead.
Yeah. Okay. So I okay after so I also checked the paper. So I have a very counterintuitive impression because in my impression I think so such a response is something very similar like the fingerprint. I think and such a fingerprint I think so it's identical and independent for each user. That means for each user, they may have, we all have the individual fingerprint and such fingerprint. So otherwise, if you don't have my fingerprint and you cannot unlock my iPhone, and I think here, so such vibration type, I think so we measured from this smartphone. I think it also should be the every user should have a very totally different vibration type, and so I'm wondering how this multi-class model and binary model and they in their further experiment how they obtain some similar vibration types that similar with the users.
I think Chenpei is offline. Let's wait for a while. Waiting him to come back. Yeah, go ahead.
Okay. Today I will present the paper FedDL Federated Learning will Dynamic Layer Sharing for Human Activity Recognition. First, let's recall how federated learning works. In federated learning, first, users will get the model from the server, and users will train the models based on their local data set, and then they will upload the local models to the server. And at the server, it will do the model aggregation, and finally, it will send back the model to the user. As some previous paper mentioned, after model aggregation at the server, we will get a new global model, but this new global model is not accurate for all users. And also, the communication overhead is very significant. So based on these two challenges, there are some new insights. First, the authors observed that there exist intrinsic similarities among users' activity data. And they did a experiment on the Hotbox data set, and we can see here exists a clear group relationship among different subjects' data. So they propose that we can learn the underlying relatedness among users and apply it to model aggregation. And another insight is the degree of similarity among users' deep models reduced from the bottom up. So in this case, we can explore such similarity of models and aggregate them in an interactive layer-wise manner. Based on this, they first conduct a case study on the real-world data set, the Hotbox data set. They first visualize the relationships among the data of 6 users from the Hotbox data set by computing the Pearson correlation coefficient. It measures the linear correlation between 2 users' data. And we can see there are obviously 2 groups here, the N1 and the N2 group, and another groups include N3 to N6. And however, the users within each group are of different degree of similarity. For example, N3 is less related with the other users in the group 2. So this observation inspires a dynamic sharing structure, while only users with similar data distributions should collaborate in learning, and the users who are more closely related to each other will share more layers of their models. So they propose the layer-wise sharing structure. This structure is derived according to the correlation matrix of the 6 users. And specifically, N4, N5, N6 should share more layers than N3. since they are more closely related to each other than N3. And they also they also compare the performance of their proposed structure with the all sharing structure and the key sharing structure, along with a baseline global method, which is the Fed average. And we can see the accuracy of the layer-wise sharing structure is much higher than the other three structures. So motivated by the case studies results, they attempt to generate the layer-wise sharing structure from user relationships to improve the model accuracy. And this is the structure of the FedDL. Initially, all the users start with the same neural network and initialize it randomly or from a pre-trained model. And after user perform multiple epochs of local training, the server will group users based on the model affinities obtained from all local models testing results on a reference distribution in terms of a common sample set. And based on the grouping result, the server will update the sharing structure. And for L layer models, here is a 3-layer model. It will perform 3 rounds of user grouping with each grouping round. And within each grouping round, it will followed by multiple rounds of model emerging within each group. To perform the model merging, we can obtain stable models with the lower layers. And after multiple rounds of model merging, the server will send the shared model to the corresponding users. And this step will repeat layer by layer. And for the process of the model aggregation, it mainly consists of 4 steps. First, the user will conduct a round of local training and upload the local model to the server. So the server will do the grouping and the merging process, and finally send the models to the users for another training round. And except for the grouping iteration, when all whole local models are uploaded to the server, most of the global communication only involves the lower layers, so it can reduce the communication overhead. Then I will introduce how the user grouping works. The procedure of the model affinity-based grouping mainly consists of 3 steps. It first calculate the affinity matrix based on using the KL divergence. We can see the equations here. The theta the theta here is the softmax output of the local model on the ith record of the common sample set. And the theta reference is the reference distribution. We take the average of the two models' output as the reference distribution. So based on this equation, a higher model affinity will cause a lower D value here. So after this procedure, we can get the affinity matrix MA, and we will also keep the, and then the it will conduct the group. It will group users based on the affinity matrix and the previous grouping result, since we keep the grouping results for the lower layers in a dictionary. And after this, it will update the layer-wise sharing structure. To specifically to group the users, FedDL will check the affinity between each pair of users and then compares it with a threshold to decide if their models are related enough to be grouped together. They take the average of the affinities between users as their threshold for the grouping. And based on the group relationship among users, it will finally update the layer-wise sharing structure. And it will stop the grouping operation when the number of groups at the layer equals the number of the users. So based on the grouping result we get before, the FedDL will merge the local models in a layer-wise manner. For each model merging round, user will perform a round of local training and upload the lower L layers of their models. And the server will weighted average of the lower layers. According to this, the frequency here is the times that a user being processed during the procedure of grouping. A higher frequency value indicates that the group member is closely related to more users within the group. And we use this weighted average coefficient to calculate the weighted average of the lower layers. And after merging the layers of the models into shared models, the server will further personalize the shared model for each user by aligning each local model with its corresponding group model as follows. To understand this part, we can see an example here. At a certain, we assume that at a certain layer, 3 users are grouped as this dictionary, and the training process produced the grouping result as this. Without the alignment, the models of the user 3 obtained from the two training process will be significantly different. But if we do the alignment according to this, the models of the user 3 and the 2 grouping result will become much more similar.
Tongnian, sorry to interrupt. For here, I don't know, your weight depends on, say, in group 1, there are 2 users, in group 2, there are 3 users, then your ratio here depends on how many users in the group, or say the ratio here depends on, say, the data size of each group. For example, if in group 1 I have less users, say 2 users, but each user have a very big data size. You know, in group 2 I have more users, but each user they have very small data size. So how can you determine the weight here?
The weight, do you mean the this value?
I didn't read through the whole slide, but my guessing is, you know, you try to determine, you try to put the weighted aggregation, right? It's not like the average federal average, everybody with the same weight, but you know, you divide them to groups, and for each group you put a weight, right, before the gradients, right?
Yeah.
What I'm asking is, how can you determine the weight? What's the weight rely on or depend on?
It depends on the size of this group.
What do you mean by size of the group? By the numbers of participants in that group, or by the data size aggregate? I mean, overall data size of that group.
Oh, it's number of the users in that group.
But it seems that it's kind of I don't know, it's kind of unfair. But okay, yeah, even the federal average is very similar. Oh, okay then. But my question is, you know, for example, like the first group, right? They have 2 users, but each of the users, they have very big data size, right? The second group, they have 3 users, right? But each of the users, they have very small data set, right? So in this case, how can you, you know, define the weight?
We will first get the weight average coefficient according to the frequency, the corresponding frequency, and the frequency is the times that users being processed during the grouping procedure that I mentioned before, and then we can get get this weight. So I think is I think the size of the data set would not affect the result.
Okay.
So what is lambda here?
This one.
What is I? For example, what is I first? Index I.
I is the ICE users.
Okay. So what is the index GLK?
This one is the model that shared by users in a group, in the case group at the else layer.
So K is the group, L is the layer. So GLK is the group of users for the case group, else layer. What are the users in this group? So what is the WGLK here?
Is the the shared models in this group.
What do you mean by shared models? So do you mean that, for example, for each group, each layer, you need to maintain a shared model?
We first conduct the user grouping procedure, and we
Yeah.
can add a group.
Yes. But the group is based on layer, or so are you grouping the user based on, for example, user 1 and user 2 belongs to group 1, user 3, 4, 5 belong to group 2? That's one grouping method. Another one is that, well, here you keep mentioning about the layer and the group key. So do you mean that, well, for each, so after you divide the users into different groups, then you further divide each group into different subgroups according to layers?
It's group layer by layer.
I think it depends on the closeness of the gradients, say, you know, something like that.
Yeah, you just use this example, okay? So this is sharing structure, right? So
Yeah.
this sharing structure,
Use a KL divergence for this WQ, P, and Q to say, but definitely there should be a threshold or a metric, you know, to determine you're going to the same group or not. Yeah.
yes. Yeah, so first thing, okay, so first thing here, this one, well, if we already consider this group, this is more like, well, for layer 1, all of the users belong to a same group. For layer 2, user 1 and 2 belongs to one group. User 2, 3, 4, 5, 6 belong to another group. But this one is basically means, well, different user belong to a unique group, right? And then, well, this is one sharing strategy. But how is this? So you mean for each layer, you want to do something like this one to build the user relationship?
Yes. For each layer, we did this.
So for each layer, you get this. How do you? So you calculate the KL divergence?
Yeah, for example, Dr. Guo, like in this layer, their KL divergence is like this, okay, 0.2. And for this layer, the KL divergence is smaller or bigger or whatever, so 0.1 or something. You know what I mean, right? They just use a metric to define, But the thing is, I'm not sure how they define, you know, how many layers you need to divide it. Is there optimal division for that? Optimal number of layers for that? Actually, that's another question I want to ask, but I think,
Oh, the grouping process will end when we reach the layer before the output layer. So the output layer will not be grouped.
Yeah, the thing is, Tongnian, for example, the original clustering class, the idea, right?
Yeah.
What is the clustering? Clustering, we just add one layer in the middle. Then it's the aggregation, right, at the server end. What do you call here is a layer-wise. It means that we make it more hierarchical. Instead of you use one cluster layer, I do it multiple layers. I divide the users, say, in 3 layers, 4 layers, whatever layers. right? Again, the clustering idea, we just add one layers in the middle between the users and the server. Your layer-wise idea is, okay, I further divide that. I divided them into multiple layers, probably more than 2 layers, right? That's the idea. So, but the thing is, my question is, in the middle, how many layers you should propose there will be the optimal number?
The layer is the number of layer is the same as the number of layers in the user's models. They did not add layers.
Yeah, I think Dr. Pan, for Dr. Pan's question, I guess from the figure looks like, for example, if their deep neural model has 100 layers, then they need to do 100 clusterings. For each layer, they do a clustering.
Okay.
Well, that's whether it is feasible or that's a different story. But my question, maybe my another question is that, how can the server determine do this clustering? For example, if they want to do for this layer, right, they want to cluster them into 2 groups. So I assume that they are based on the output from this layer, right, Tongnian?
Yes.
So is this what they're doing here? They are for example, because you have, 6 users. Oh, sorry.
I think Tongnian has a 1 page to show what the server is doing, right? So the overall procedure. Tongnian, could you go to that page to show Dr. Guo? The overall procedure page.
How the server, yeah, I think
this one.
Yeah, this one, yeah. So let's say you are the server, right? While you received what you receive from the user here.
You just receive the gradient, right? So I think it's not the, I don't know, it's very confusing. It's not a training layer-wise division. You receive the gradients somehow based on the updated gradients, you group them. That's my understanding. Similar to the clustering and stuff like that, yeah.
Sorry, my network was, I didn't hear you.
Yeah, so let me see. Just I think Dr. Pan's question and my question are the same, saying that, well, what has been uploaded by user to the server in this scheme? So for example, the step 2, right? The step 2 is that while you receive the model, you do some kind, or what you receive from the server, or that's a lot of question. What you receive from the server, what you upload to the server.
So first, before the whole process, we will initialize the user's model and upload the whole model to the server.
Okay.
And the server will do the grouping, and we can get the sharing structure.
No,
the
here.
server is going to group him based on what? Yeah, that's I think that's both my and Dr. Guo's question.
So it will, so for if the original model is L layer, the grouping, it will perform L round of user grouping, but within each grouping process, it will followed by multiple rounds of model merging, and in the model merging process,
that's the method, Tongnian. That's the method. So what we are doing, what we want to clarify is not the method, is the input. So for example, well, you say for each user, I just submit my trained model to the server,
I know
Understand.
I didn't explain to that.
Uh-huh.
So in the merging process, the user and the server will transfer the lower several layers. So only the first upload procedure upload the whole process, and later they will only transmit the lower several layers.
Oh yeah. That's true. That's after you get this tree structure, right? For example, after you get this tree structure, of course you know, well, for example, everyone share this one, so I will only transfer. So everyone share this one, so everyone will transfer this layer. And you know, well, N1 and 2 they will share this one, and 3, 4, 5, 6 they will share this one. So maybe only N1 and N2 they will transfer this one to each other, and 3, 4, 5, 6 they will transfer this one to each other.
Yes.
But we are talking about the communication between the user and the server, right? So no matter whether you are belong to this group or this group, user 1, user 2, they still need to transfer this L2 layer to the server. It doesn't matter. I want to transfer my layer L2 to 3, 4, 5, 6. That doesn't matter, because what I care is the communication between myself and the server, right?
What's the original motivation for this paper? I mean, if you only want to do the grouping, that's fine. But the thing is, say if you want to do communication efficiency, right? You want to save the communication cost. You transmit things like this layer-wise, one layer by another layer to the server. It may not necessarily reduce the communication cost, right? Although you do the grouping, probably not everyone submit, you know, only the cluster head or whatever.
Yeah.
But still, it's hard to evaluate. It's not necessarily reduce the cost though. At least from the downlink from the server to the user point of view, you know, you need to do more times.
I think from Tongnian's explanation before, looks like what they are doing is trying to do a personalized federated learning. So this belongs to personalize the personalization, and then communication efficiency might be a secondary concern, I think. But their major focus will be personalization, and they are trying to, for example, they believe that N1 and N2 their data are more similar, so they communicate more. While N3, 4, 5, 6 they are more similar, so they will share their model more. And those two groups, they will only, for example, they may only share the bottom layer or things like that.
Yeah.
Well, that's my understanding. But then I was trying to find out, well, I think the first thing is that how can we calculate this using the KL divergence, right? How can we do the clustering? That's the first thing. Second question, okay, given that I know this, how do I implement this on a practical system so that it meets the communication efficiency requirement? I think those are two different questions. So first thing, let's figure out how do they do this kind of clustering here. So let's say start from the beginning, right? Start from the beginning. While the cloud they have an initial model. They send the initial model to each user. Then what do they do now?
The local user will train the model and upload the model to the server.
Yeah, so the server loads that, well, after you train, you load each user's model, right? Individual model.
Yeah.
And then what do you do?
The server will first group the first layer of the model.
Yeah. Okay. So how do they group the first layer? So what do you mean by group the first layer of the model? Because everyone, for example, everyone has a model, right? Everyone has a model like this. And then what do you do? Okay. Then the server loads this user's model, this user's model. Okay. Then you want to group. What do you mean by group here? You mean, well, how, first thing, yeah, go ahead.
Using the KL divergence.
So they use the KL divergence to calculate the distance between those two between every two users on each layer.
Yes.
So okay, so then for this one, let's say for this layer, what do you mean by calculate KL divergence? You give them the model, right? Every user, this model just has some model parameter, So you mean that you are going to calculate the KL divergence between those two parameter factor?
The input of the KL divergence is the the output. They first they have a common sample size.
Okay. Yeah. So they should have some public data, right?
Yeah.
The server has some public data. And then I assume, okay, according to you, I guess, you just correct me, okay? I'm just guessing.
Okay.
So they have some public data. They load each user's model. And then they use each user's model, apply it to the public data. So you will get an output from each layer, right?
Yes.
So then you mean that their KL divergence will be calculated based on the output from each layer on the common public data samples.
Yes.
Okay, they want to calculate the similarity, whether they are similar or not.
Yeah.
Okay.
The
And then
server
they do
here-
that. Okay, I see.
The server here knows the neural network structure of all the users, right?
Yes.
So they can. Oh, okay.
Okay, I see. So the key is that they should have some public data set. They want to evaluate, they can use this public data set to test the similarity between different users' models.
Yeah.
Okay. And then, so for example, in this case, well, in L1, so for this clustering, also for L1, they say, well, most of them, they may have the same similar output. So they group them into a single group.
Yeah.
For layer 2, they say, well, N1 and 2, they're similar, N3 and A6, they are similar. So they divide into 2 groups.
Yeah.
So L3, they divided into, I think it's 6 groups, right? Each
3 group.
Or 3 groups?
N3 and N4 and 5 and N6.
So if it is 3 groups, why don't they just put it here? Put something here like this. I mean, graphically it's like this, right?
Yes, they just want to show how it works.
Okay. So it's actually just 3. This one is actually just 3 groups.
Yeah.
So finally, the output layer maybe just 6 groups because there are 6 users, right?
Yeah.
Oh, okay. So for this clustering tree, do they update it? For example, at the very beginning, right? At the first round, you gave them a model, the user just update it. You just update it for several epochs, for example. And then you send it to the server. Server will do this. And then next round, does the server do this again? Based on your...
The server will first group 1 layer and then the server and the user will transfer this layer of model, and you will conduct multiple training round at the user side, and then the user will upload the model, the user will then upload this layer to the server and then do the next layer.
Oh, so you mean at the very beginning, they actually first group the first layer. After they group it, they will retrain. Then they focus on the second group, second layer, and then the third layer.
Yes.
So this is before the training, right? Or I mean,
the
so
grouping is before the training.
Before the real training, they
Yeah.
just it's more like a pre-processing. They're just trying to figure out, learn this structure.
Yeah.
Oh, so those are. I see.
I have another quick question. So this layer by layer, they're independent or they're correlated? I mean, for this kind of division, should we follow like a tree structure like you show here, or this layer and the previous layer, they're independent? For example, for layer 3, I can group this 3 together. You know, yeah. Can we do something like that? They're independent, or say that's not a good example. We can group this 2 together. They belong to different group in layer 2, but in layer 3, we can do it independently. Or they follow certain kind of tree structure, like a binary tree here, or whatever tree here, tree structure here. You know, your previous layer somehow determine how many participants of higher layer.
I think the different layer, they may have different KL divergence. So
they're independent. They're independent. That's what you mean, right?
I think so.
I think the pan question is pretty good. I agree. I think they may use a tree. Looks like if you see the figure, for example, if they already divided in the layer 2, they will divide. Then they will only consider will further divide this one and further divide those 4 into different groups, similar like that.
Not very sure.
Yeah, if you see the figure, okay, I think later you have a lot of figure, like 3 figures. Looks like if it depends on what do they. For example, if this one, they're the same group in the layer 3, looks like it's weird. How can they? I feel that it's they may have some kind of assumption there.
Maybe they just want to show us clearly how it works.
But still, can you illustrate, enlighten us, you know, if you want to do the layer-wise training, clustering and grouping, whatever, what's the benefit we can get from here?
The benefit, first benefit is when doing the model merging, they generate the personalized model according to each users. And another benefit is that the user and the server only transmit the lower layers, so the communication overhead might be reduced. They did not transfer the whole model between the server and the user during the actual training process.
Oh, so you mean for this figure, you mean they transmit only this part? For user 1 and user 2, they only transmit this part to the server 1, to the server. And
no,
for those, Yeah.
For each layer aggregation, the server should do that, right? For each layer aggregation. For layer 2, layer 3, layer 4, for each layer's aggregation, server should do that, right? Or cluster head should do that. Group head should do that.
I didn't get your point.
Say, okay, like Dr. Bo show here, in layer 2, right? There's a user number 1, number 2, they're grouped together, right? For this aggregation, should the server doing this aggregation, or should it say either user number 1 or number 2, they're taken as a group header, they do that?
Oh no, the server do the aggregation.
Do all that aggregation in each layer.
Yeah.
They do the aggregation separately for different group also. I believe so, because according to your architecture figure here, you know, your broadcast model is not one, it's like different colors, right? So yeah, okay.
Yeah, I think so. I think so.
According to a different group, okay, yeah.
Then how can they? So the way that they can save communication is that after certain, for example, after this L3 layer, because each user, they will have their individual layers. They will not share with each other. So you don't need to transmit those parts. You only need to transfer the bottom part where users will need to share their models.
Yes.
Okay. Oh. Well, anyway, let's say, maybe let's say their final result. You know, they can create those solution. That's fine. Well, maybe this is the style of sensors or Mobises, those kind of system papers. They create some kind of heuristics and do a lot of extensive experiment to say, well, the performance is good, and then but there's no theoretical reasoning there, or that they don't have rigorous analysis or things like that. Or maybe this is a different style of research. Anyway. Yeah, you can just go ahead if you don't understand.
I still didn't get it. If you do this kind of layer-wise things, you can make the, I don't know, different groups, they converge faster. They don't use the upper layer or further aggregation or further training. I even say, for this example, I use the bottom 3 layers. It's good enough. I don't use further layers for training.
Yeah.
Is it what do you mean? Oh, okay.
I think they still use they still train every layer, but they just assume that different users, for example, only those layers, they're actually shared by every user, so it belongs to the global model. So they only share this global model, and then this one is more like an individual add-on, add additional individual layers, things like that. Yeah.
Oh, I got your point. So from the 4th layer, it's more like individual personalized.
Yeah.
For the lower 3 layers, I still need a global model. Okay.
Yeah. So they only need to share the global model, right? The individual model, they're different, so they don't need to train the same global or individual model. They just need to train the a same global shared model.
So for the 4th layer and above, they just train locally. They don't.
Yeah. I think so. I think so. That's what they are trying to do. That's more like a personalization thing.
Okay. Yeah, Tongnian, please go ahead. Thank you.
Okay. So they then conduct the experiment using the data set they used are these 5 data set.
Are those data sets open? You know, I mean, are they openly accessible?
Yeah, they are available.
Oh yeah, okay.
And they these are the baseline model. One is the Fed average, and the FedDL is they use the users share their lower K layers and leave their upper layer user specific. And in their experiment, they set the K to be 3, which means the shared model would be they will share 3 layers. And the PFED-ME is a kind of personalized federated learning, and it updates the global model similarly to the Fed average, but is personalized. And another one is the local training. The first conducted validation on this data set, and we can see the FedDL out. The accuracy of the FedDL is higher than the other 4 method, and the communication overhead compared with the Fed average and the PFED-ME is greater.
Tongnian, do you so for example here you're talking about the accuracy. How do you evaluate the accuracy here? Because you don't have a shared, you don't have a single model, right? You have for n users, you will have n models. And then are you going to, for example, for each user, you test the accuracy, then you take the average?
I think it's the average of all the users.
So each user, they will have their different test data set. I mean, because according to the why, how can we do they show that, for example, how do they partition the data across or among the users, or the data set is literally user partitioned?
They showed how they process the data.
So each user, they have a training data set and a testing data set.
They didn't show it, but I think so.
Tongnian, I want to understand correctly. So for the FedPer here, they just use the lower three layer, right? So for FedDL is their scheme. They're more flexible for how many layers they share, right?
Yes, it's more flexible.
Also for the FedPer, they don't do the grouping stuff, right?
I'm sorry?
For the FedPer scheme, do they do the grouping?
They just group all the they did grouping like this. All the users share the same.
Oh, okay, share the same. Okay, yours is more complex. Okay. So your cost more communication. Okay.
Yeah, but I have a question here. So for example, for the FedDL, you have a lot of, or you can do the grouping, that's fine. but you also have the grouping there. The grouping stage actually takes a lot of computation and communication resource as well, right? Because you need to keep interchange or keep updating your models and train your model, send it to a server do the grouping, then send it back to you, then you do it again and again and again. I mean, this overhead is also very high.
Yeah, yeah, I think so.
No, I think probably like you explained before, Dr. Guo, the server can do this, right? The server can do that from his end.
Yeah, but the grouping or the clustering process is done by the server, but they still need to interact with the client. Looks like you need the client to use their model to train or use their data set to train the model and then send the model to the server. Server do the grouping or clustering and then send it back to the
you're
right. According to Tongnian's explanation, they do this kind of clustering iteratively. It's not a one shot, it's multiple shots.
So the communication round in this data set, communication overhead in this data set is not greater than the FedPer.
But what do we think is probably will be more than the federal average and the federal mean, P-Fed mean. It's not necessarily less than them. That's I think what we our question. Yeah.
I don't know. Yeah, basically, for example, if you have a lot of layers, right? According to Tongnian said, well, if you have 100 layers, then you need to do those the training, the clustering process takes 100, at least 100 rounds of communication. That's extra communication. And if you talk about privacy, then that's a big issue as well, because you increase your the usage or the frequency of the usage frequency of your data.
Yeah, probably if it's more than 3 layers, less than, I don't know, probably 10 layers or something, will be more efficient than federal average. But if it's like you said, it's a 100 layer deep neural network model. Yeah, it's hard to say.
Yeah, so I think they may have some kind of tuning, in their experiment. They tune it, make it work under some special cases. There must be some kind of when they do the experiment, there may be some kind of they will consider this. They will know that what's the under which situation that their method can work, but they may not show it.
Is there any typical model to train this HAR data, Tongnian? Say how many layers they choose or something? Is there any kind of typical deep neural network model they choose?
No, they didn't show it in their paper.
Okay, probably that can.
But they should talk about
Yeah, that can answer Dr. Guo and my question, right? So typically they say they choose a 10-layer deep neural network model. So whatever model, ResNet or whatever, then probably they can further justify, okay, I can save some communication cost compared to the federal average. But anyway, that's our guessing though.
Yeah, I guess there are a lot of tuning. Yeah, maybe you want to repeat the results. Well, you do a lot of things, and maybe you will find out only under some certain, settings that you can repeat their results.
Yeah, for communication.
No, that's normal. Yeah, this is experimental research. Right?
I think in their experiments, they just use 2 convolutional layer, 2 collected layer, and 1 softmax.
So it's very small, very small.
Neural network, yeah.
Oh, okay, I see. Yeah.
Go ahead, please.
Oh, okay, and then they compare the performance of this 5 model in this 4 data set. The accuracy of the model is higher, and the variation is also reduced significantly. And for the communication run overhead, it performs better in the UWB dataset and the depth images, because these 2 datasets are more hierarchical.
So their method is always better than Fed averaging and the P Fed me, but it's less than Fed per, right? Percent. It's larger than Fed per.
Yes, larger than Fed per in some data set, but it's lower than.
Oh yeah. I guess that's what Dr. Pan and my guess is that, you know, under different models and different data set, they may have different performance.
Also, their layer chosen, how many layers they should choose, it's kind of a dynamic. It depends on the data set and model.
Yeah.
I believe, yeah. Wait, their testing accuracy is always better than everyone?
Yeah, I think it is.
Yeah, I mean, sometimes I feel that it's very hard to compare those different methods. Well, it's maybe very easy for you to compare the Fed averaging local, but P-Fed or Fed Pro, or they have their own tuning, their best
Yes,
settings.
exactly. Yeah.
And then you know, unless you tune those kind of baselines into their optimal setting, and then you tune your own method to your optimal setting, then you compare the two, maybe it's convincing. But I believe most of the cases that they also will not do that, just because, you know, tuning one method takes a lot of time. Yeah, I feel that usually what they do is that maybe they just you know, use the same setting for all the baseline, and then sometimes this setting may be favorable towards your own method.
Yeah, I agree. At least,
I think your microphone may have some issue.
yeah.
We cannot
Oh,
hear you.
okay. Can you hear me now?
Yeah. I know you're saying they need to well tune the model.
Yeah.
But I have doubts, right? So for example, Fed per probably, always inferior to your FedDL. But for Fed me, I don't know, they are both personalized training, right? So FedDL, the only thing you do is you do the layer-wise things. But it's not necessary say FedMe should be worse than the FedDL. I didn't quite get why it's always worse than that, because if you consider the data diversity, FedMe consider data diversity, the only thing they didn't consider is the layer-wise thing, right? So if you say, okay, your FedDL saves the communication cost compared to FedMe, yeah, I can partially agree with that. But for testing accuracy, is it always like that? I really doubt. But anyway, that's my doubts. Is like Dr. Guo said, probably you need to well tune, then you can do the better comparison. Because I cannot find a very intuitive, reason why FedDL is better than FedMe.
Yeah, I agree. There's no rigorous analysis, there's no intuitive intuition that can explain this before you do the experiments, right? They only rely on experiment, but experiments there are a lot of things, a lot of randomness there.
Yeah. Okay.
Yeah, just go ahead.
Okay. And then they evaluate the scalability of their model. They train the data from the 30 users, 60 users, and 90 users, and they found their method improved the model accuracy for most nodes, and it maintained a relatively low communication overhead. And finally, they evaluate the impact of the local communication round, and it shows that a larger value of local communication round will improve the performance on the accuracy and the communication overhead of both the personalized and global models. And it converge fast when even their model converges fast even when there is a small number of local communication rounds. So the advantage of their design is that it reduces the number of parameters that each user uploaded to the server, and it can reduce the number of global training runs because it converges faster. And that's all.
Let's skip the stupid question session today. Okay, it's already 2 hours. So any other questions?